Welcome to Trigonometric Equations Part 2, and we encounter our friend Mr. Tan. And so let's solve him. Tan of 2x equals root 3. Now remember, the one thing you have to remember about tan that's different from cos and sine is that the period of just the normal tan function is actually pi rather than 2 pi. Why is that? Well, sine over cos is going to be exactly the same value as negative sine over negative cos. So instead of having a value just occurring once every 2 pi, you're going to have the same value occurring because it's a slope. You think about your unit circle, which looks like this. If we think about all the same slopes that we have on that unit circle, we always have two regions. We've got this region here and that region there. They have the same slope. And that one there and that one there had the same slope. It's a bit wonky, but if I could draw, that one there and that one there have the same slope. So for every tan value, you're going to get two values, repeating at pi rather than repeating at 2 pi. So with that, let's solve this little chap. So tan 2x equals root 3. I'm just going to go and let x equal 2x. So I'm just going to get rid of that 2x, and I'll do that whatever value I have in there really. I'm always just going to get rid of it. Okay, and just go straight in for tan of x equals root 3. Just makes it a little bit more straightforward. So then over in my calculator, I do tan to the negative 1 of root 3, and I would get pi on 3. Okay. So therefore I know that x must equal pi on 3 plus k pi, because it occurs every pi rather than occurring every 2 pi. So therefore now I'm going to sub back in. So I get 2x therefore is going to equal pi on 3 plus k pi. And so x is going to equal pi on 3 times half, or divide by 2, so that makes it pi on 6 plus k pi over 2. Now we just have to think about our domain, and we know that it's in between 0 and 2 pi. So with that we can just think, well, k 2 pi over 2, I'm just going to write this out over on the side. You might be able to work it out without doing this, but it will just make it a little bit easier. So k pi over 2 is the same as k of 3 pi over 6. So basically I'm just going to add 3 over pi over 6 to pi over 6 until I get something that's going to be greater than 2 pi. So I'll stop at that point. So if I add 3 pi on 6, I'm going to get 4 pi on 6. And if I add 3 pi on 6 again, I get 7 pi on 6. And if I add 3 pi on 6 again, I get 10 pi on 6. And then we're done, because then I'd get 13 pi on 6, which is greater than 12 pi on 6 or 2 pi. So I could simplify those a little bit. Pi on 6, 2 pi on 3, 7 pi on 6, and 5 pi on 3. And there's our answers. Solving this one. Well, this one looks a little bit unhappier, but it's not really, because you can factorize. Remember that when you're solving an equation equal to 0, you can always factorize, take out the common factor. What is it? It's sine of x. Sine of x appears in both terms. So I'm going to put sine of x out the front, and I'm going to get sine of x bracket 1 take square root 2 cos of x is going to equal 0. So then I'm going to use null factor law, which says that if you've got two things multiplied together, one of them has to equal 0. So sine of x equals 0, or 1 take root 2 cos of x equals 0. Now this time I don't have any domain, so I don't have to worry about that. I'm just going to get, well, when sine of x equals 0, x is equal to 0 plus k pi. Now normally, of course, we add k to pi, but remember, when we've got sine of x equals 0, we're at this unique stage here where it's got those two solutions which aren't just separated by 2 pi, they're separated just by pi. And then we can solve the other side. So x equals 0, or 1 take root 2 cos x equals 0. So that would mean that cos x is equal to negative 1. And I'm just going to leave that there. So negative root 2 cos x equals negative 1. And therefore cos x equals negative 1 over negative root 2, which equals 1 over root 2. Now I can just put that in my calculator and do cos to the negative 1 of root 2, or I can think about my unit circle and go, well, 1 over root 2, that's actually... So that's there and there. Really, really bad circle there. But you can imagine the two values. And so if cos of x equals 1 over root 2, we can know, well, that if we look on our unit circle, we just have to remember that 1 over root 2, if we multiply that by root 2 on root 2, so if I multiply that by that, because root a times root a equals a, if you've done surds, you'll remember that, okay, then root 2 times root 2, that those denominators multiplying together actually equals 2. So we can see from our unit circle, therefore, that x equals pi on 4 plus k2 pi, or instead of what we had before, it's going to equal 7 pi on 4 plus k2 pi. And there are our two solutions for x. So x can be all of those values.